Well, good morning, everyone. Hopefully, this week is finding you still well, and looking forward to doing a little bit more modern physics. So, if you're here in the chat, please give me a little thumbs up or something like that, so that I know that folks are present. But today's going to be a little bit of a review, so I'll start that and wait for questions to pop up in the chat. Just so you know, just to remind you all, today we're going to be reviewing a little bit about the ideas behind chapters 6 and 7. Chapter 6 covering the material introducing the idea of the Schrodinger equation and the solutions to it. And then in chapter 7, we apply the Schrodinger equation to the problem of solving for what the state of atoms would be like. And we hopefully learned a bunch about how, or why, in the idea of quantum mechanics, why Bohr's idea of the atom actually came out to be true. Turns out that there's a lot of things behind what the reason why Bohr's theory of the atom came out to be true. But it's interesting that sometimes those basic ideas that Bohr came up with for the Bohr structure of hydrogen turned out to sort of still be true, even when you account for the details of quantum mechanics like Schrodinger talked about. So just to remind you, the Schrodinger equation looks something like this. It says that this is in one dimension, but negative h bar squared over 2m. This is what we would call the kinetic term. Relates to the square of the momentum. E squared psi dx squared. And then V is the potential. When you multiply that times the wave function, then this is the potential energy term associated with it. And this is where the time dependence has been separated out. So equal to E times psi of x. And this is, of course, here also a function of x. So what I think was what our beginning was with this is to say, well, let's look at the simplest solutions possible. So the beginning, what we were talking about was really what everything is talking about is we need to look at what the potential is. The potential is what determines what problem you're solving, basically. Everything in the Schrodinger equation stays the same, except the potential energy function that the quantum exists in. So the potential energy functions that we started with were, well, let's look at a function of x, which is a square well, but infinitely high. That was the particle in the box problem. So you should know something about how the particle in the box solutions work. And so this is sort of reviewing, like I said, chapter 6. And so that was one potential that we dealt with. And it's a good potential to start with. The solutions are relatively simple, and they give you some idea about how quantum mechanics works and how we can use the mathematics of differential equations to figure out the physics of particles that are confined. In this case, the confinement is complete. The particle cannot escape the box because the potential is infinite. And it showed us all sorts of information about how particles behave when they are 100% absolutely confined. Then we started to look at other situations. So we had the particle in the box. Then we dealt with the particle under the influence of a harmonic oscillator potential. The potential we used was 1/2 m omega squared. And that's the same as 1/2 kx squared, if you remember that omega is the square root of k over m from classical physics. We can also write that. So the solutions to the harmonic oscillator potential turned out to be much more complicated, showing us that even when we take a small step up in complexity, the mathematics associated with quantum mechanics can really ramp up quick. So the solutions to this were exponentials, not complex exponentials. It was a Gaussian potential, or Gaussian, distribution. So it was like e to the something negative x squared, and then there were polynomials that multiplied the Gaussian that Gaussian exponential function. And then we found that for this potential, there were, because of the application of the boundary conditions and all that sort of stuff, there were, again, energies associated with each individual wave function. So it was an eigenvalue problem. The energies corresponding to n plus a half times h bar omega, where mn, can have, as an integer starting at 0, 1, 2, etc. Okay, and then the wave functions are more complicated. It was the wave functions associated with any one where I'm going to try to draw. There's some c sub n, which is has to do with the normalization constant, and then there was, let's see if I can sort of draw. This is that's a special h. That's the Hermite polynomial of the nth order, and then there was an exponential. I don't remember. I have to look it up now, but it's something like e to the minus some bunch of constants. I'll just put that in there, times x squared. Okay, or times. I better look at it. I better look. We better consult the tome here. Let's see the Schrodinger equation. Let's see the finite square potential, simple harmonic oscillator. Here we are. And this is, let's see. Yep, it's e to the minus m. Yeah, it's some minus m omega over 2h bar is what that constant is, times x squared. So that's what our wave functions look like. And these Hermite polynomials are special polynomials in x. All right. And then, so that was the harmonic oscillator potential. And basically the idea then is we see that there is a lowest energy. It's not 0. The lowest energy associated with the harmonic oscillator potential corresponds to n equals 0. It's equal to 1/2 h bar omega. And you will notice that as that this implies that even when you take the situation where I have the lowest possible energy, the particle still has an energy. It's not 0. And that means that any bound particle so far that we've seen has an energy which is not 0. Even for the particle in the box, the lowest energy that produced a particle had n equals 1, and it had a non-zero energy. So that tells you something interesting in quantum mechanics, and it has an application in thermal physics about something that people sort of knew about before this but didn't really understand why. If you have particles, any particle that is in a bound state, at least of the two examples we've dealt with so far in one dimension, as you get the particles to settle down to their lowest possible energy state, you will see that that energy is not 0, which means that there will be some kinetic energy associated with the particle. In other words, it doesn't stop moving. Now, if we interpret the temperature of an object to be the average kinetic energy that the particle has, and that is what the kinetic theory of matter states, is that the temperature is related to the average of a substance is related to the average kinetic energy of the particles within it, then this is telling us that even when you cool the particle all the way down as low as it can go, there's still some residual kinetic energy in the substance. And that basically tells you why absolute 0 is an unattainable goal. Because even if I were to take because absolute 0, when it was defined, was the temperature at which all molecular and atomic motion would cease within some substance. That's what that extrapolation down to temperature 0 was. And quantum mechanics now tells us that it is actually technically, but realistically and technically, impossible to get down to the lowest possible temperature of absolute 0. So that's kind of an interesting circumstance. It tells us why we can asymptotically approach absolute 0, but you can't actually reach absolute 0 because the energy of the particles will never reach zero, at least in one dimension. But in 3 dimensions, it doesn't make it less true. We found out in 3 dimensions it actually is, it still has that same limitation. So that's the sort of look that we can expect there. So the other thing that we talked about in the other things that we talked about with regard to this is with the Schrodinger equation is recognizing that it is an eigenvalue problem. And the way sometimes to calculate, or the way to think about these problems is that this works only for specific energies and specific functions that go along with each of those energies. So that's why I wrote down that there's an E sub n, where n labels which energy we're talking about, and then there's a wave function that goes along with that as well, psi sub n. And then we talked about the idea of operations, operators. So the energy operator, well, let's talk about expectation values and stuff like that. So the expectation value of a particular operation is found by, so this is what we would mean. So let's say I have an operator, let's call the operator, just for our purposes, let's call the operator F. Okay, and I'm putting that little hat on it to indicate that it's an operator. It's not the eigenvalue, it's actually the operator. So then what you would have is that you need to integrate over so I've got a particular wave function which might not be an eigenvalue here, or an eigenfunction. So this is starred actually. It's the complex conjugate. And I have to integrate over all of the wave function for all points. So this is what we call the expectation value of the operator F. So what I do is, what I'm taking is I take whatever wave function I'm talking about, psi star, and I complex conjugate it. So anytime, every time you see the imaginary number I, you turn it into negative I. And then I operate on that wave function with the operator. Now, if this is a really simple operator, like it's just a multiplication, then you can just do psi star psi and then have the operation come out. But if this is an actual operation, like for the momentum operator, it was actually, remember, differentiation. So I have to differentiate psi, operate on psi with it, and then multiply the result times psi star to integrate that result from minus infinity to plus infinity. There was sort of a shortcut here if we can express the wave function in terms of a linear combination of these things. It just becomes the weighted average. And we did example problems on that. So that's an important thing that I think you should probably concern yourself with, is being able to perform these expectation values for particular, for wave functions. So being able to perform either these integrals or using the completeness conditions on the wave functions to be able to perform the weighted average. So I think that's a really important thing to be able to do. And remember what the completeness conditions were on this is that the completeness condition on this wave function psi sub n is that let's see if I can remember the details of it now, but basically it's the integral from minus infinity to plus infinity. That's supposed to be a plus. Okay, there we go. Of psi n times psi m, both of x. If I integrate this from over x from minus infinity to plus infinity is equal to 1 if n equals m. This is if they're normalized. So in other words, this is actually a star. Okay? Because this then becomes psi n squared times psi n times psi n. So this becomes psi squared, and then you integrate from minus infinity to plus infinity, and if it's normalized, that would be 1. Okay. But it would also be 0 if n is not equal to m. So in a lot of ways, this is like almost like a dot product, but in an infinite dimensional space. If you think about it, and what then you could do is if this operation changes, then you can look at the this. So it's possible to use this operation and then use this condition here to turn this into a weighted sum, a weighted average on the wave function. Okay, so just to sort of remind you about how that worked. And so again, if there are folks here, just give me the thumbs up to let me know that you're here. It looks like I might have a viewer here, but I'm not exactly 100% sure just yet. So so know how to do these style of problems where you're calculating the expectation value. That's an important thing to be able to know and to be able to do. So being able to normalize wave functions, know what that means. That's an important feature. And then, so yeah, I think that's sort of the way to look at that. So that's basically what I would regard as sort of the most important highlights of Chapter 6. Chapter 7 introduced some complication into this. And the way that it introduced complication to this is it said, well, let's not just do one dimension anymore, let's do 3 dimensions. And the style of potentials that we started out doing is said, well, let's do a 3-dimensional particle in the box. So we're going to say that in addition to there being a v of x, there's a v of y and a v of z. So the particle's in an actual 3-dimensional box. And then we're going to say that the wave function is a function not just of x, but also of y and z. And we turn this into a 3-dimensional version of this with 3 derivatives with respect to, one with respect to x, one with respect to y, one with respect to z. V is a function of x, y, and z then, and then we solve the problem. And then what we looked at was the fact that the wave function then could be a separable one, where the wave function has has multiplicative components to it, that it says that the wave function has to do with psi of there's a x piece times a y piece times it. So we're just guessing that would be true, and we found that it was separable, that we could separate it out, and we were able to turn it into 3 one-dimensional problems. And of course, since we'd solved the one-dimensional box problem, we knew what the solutions were. So we could kind of add them together and add the energies together to get the total solution, and we could multiply the individual wave functions of x, y, and z together to get the total solution. But this introduced an idea that the particles could, the wave functions, different wave functions could have the same energy. So the idea of the wave functions and the energies being degenerate was an important thing to notice. So there was degeneracy, and remember that degeneracy means specifically that there is more than one distinct wave function that has the same energy as the other. So the example of the 2-dimensional particle in the box, just to remind you about what that. So the particle in the box problem said that we had, you have n1 and n2. So this is 2 dimensions. There's a function of x and y. And it says that the wave function is, I think it's still square root of 2 over, I don't remember. This is, we'll just say that this is the, this is still the normalization constant, but it's the sine of n1 times pi times x over, let's say it's a square box so that L is the same in each direction, times the sine of n2, n2 being the quantum number associated with y, over L. Okay. And then the energies which depend on n1 and n2 also are, in this case, let's see, it's h bar squared pi squared, and then there'll be an n, but we'll put that in there in a second, over 2ml squared. L is again the size of the box in each dimension, and then it'd be n1 squared plus n2 squared. Hopefully you sort of remember this idea, but I'm trying to remind you of some of these important highlights. Notice that if n1 is equal to 2, and let's say n1 is equal to 1 and n2 is equal to 2, okay, that has a particular energy. It'd be, 5 here. But the same would be true if n1 is equal to 2 and n2 is equal to 1. It's the same energy. But notice that that's a different wave function, because when n1 is equal to 1, the x dependence is pi x over L, sine of pi x over L. And when n2 is equal to 2, it's sine of 2 pi y over L. So the y dependence has that, the 2 pi in it. But if I switch and say n1 is equal to n2, notice that the x and the y dependences are different. So it's two different wave functions, but they have the same energy. No matter which, if you got n1 is 1 and n2 is 2, as opposed to n1 is 2 and n2 is 1. So I have the same energy for two different wave functions. That's what we call degeneracy. So that's an important thing to note. So the idea of degeneracy ended up being really important. Then we said, well, let's start to consider the situation where things get more complicated. Well, let's actually simplify a little bit to an extent. We're going to say that our potential only depends on the separation between the two particles. Now, this obviously is with an eye towards solving the hydrogen atom problem, because that is the potential where the potential energy between an electron and its and the nucleus at the center, that potential would be kq over r, kq squared over r squared, or ke squared over r squared, where r is the separation between the two. But it doesn't matter what angle it's at; it just matters how far they're separated. So that's one type of potential where V only depends on the separation. So this is what we did. We said, let's put the nucleus at the origin. And let's say the electron then is at some position relative to that origin. And we're going to, since the potential only depends on how far they're separated, it seems plausible that we should consider what the Schrodinger equation would look like if we expressed it not in Cartesian coordinates, but in spherical coordinates. So that separates out the theta and the phi dependence, and the potential only depends on r. Okay, so that seems like a pretty broad class of problems that would be important to know the solution for. So that's what we did, and the problem was not simple, as we saw, but it is solvable. It still is basically exactly solvable. We said that the theta and the phi dependence always then separates out and gives rise to the kinetic terms of when the particle has angular momentum. So it's angular momentum that ends up popping out of that particular part of the equation. And then the radial version of the equation that involves the potential actually then is a one that's specific to this one, where we got the 1 over r 1 over r potential energy function. And that potential energy function then gives rise to the radial equations for the hydrogen atom. Specifically, we got energies which look like the hydrogen atom energies that Bohr predicted way back in the day. And the wave functions are complicated functions of r, theta, and phi. But we were able to show, and this was one of the homework problems that that you've seen, we're able to show that for the ground state, that the wave function has a peak at the Bohr radius. Just what he predicted. It's not what the average is, but it is that at least that's where the peak, the maximum probability is. And then there were different states, different orbitals, where n is different. But notice that n, the principal quantum number here, which governs where the radial distribution, that provides limitations on the angular momentum. So remember how the Bohr, or how, not how the Bohr, but how the hydrogen atom looks is we say that n is an integer starting at 1 and being any positive integer, and it can't be 0. Then the angular momentum, the conditions on angular momentum say that the angular momentum quantum number can go from 0 up to n minus 1. Okay, so I'll just put a little dot there. So it's all the integers from 0 up to n minus 1. So those are the values that the orbital angular momentum quantum number, the value of L, which that was one of the separation constants that came out of the angular separation. It's associated with theta. And then the phi one this is the magnetic quantum number. The magnetic quantum number, its boundary conditions are that it must be all integers between negative L and positive L. So these are the quantum numbers that are associated with any electron in the hydrogen atom. N always starts at 1, which means that L must be 0 if n is equal to 1. And then M must be 0 as well because it's negative 0 is 0. So there's only one value. So the 1, 0, 0 state of hydrogen is the lowest possible energy state. And it's the one that we can calculate what that energy would be. It's the Bohr energy. But then there's the case, well, what if we have n is equal to 2? Well, now things get a little bit more complicated because L could be 0 or L could be 1 because it's all integers between 0 and n minus 1. And with n equals 2, I could go all the way up to 1. All the way up to 1. When L is equal to 0, M still needs to be 0. But when L is equal to 1, then M, the magnetic quantum number, could be negative 1, it could be 0, or it could be positive 1. So that gives rise to the fact that we've got the splitting of the angular momentum. So the angular momentum could have different orientations. So you should also know how to treat angular momentum in the situation in the hydrogen atom. The angular momentum in general, where we have any. So if this is these axes, then we've got this is positive x direction, this is positive y direction, and this is the positive z direction. Then remember that the total orbital angular momentum, L, has a magnitude of the square root of the quantum number L times L plus 1. Those are supposed to be L times L plus 1. So it's the square root of that times h bar. And then L sub z, the magnetic quantum number is m times h bar. So notice that not all orientations of the angular momentum are allowed. You have specific ones. So if L is equal to 1, then the magnitude of the angular momentum quantum number, or the angular momentum, the quantum number is L is equal to 1, but capital L, the angular momentum itself, is the square root of 2 times h bar. L sub z then could be either positive h bar or negative h bar. And because of that, notice that there's specific values. I think this is, so it could be, this could be the you could have 45-degree angle here, or you can have negative 45 degrees with respect to this. So the angular momentum orientation can either be, this is for m is equal to positive 1, and this one is for m is equal to negative 1. So, and then of course there's different ones as well. If L is equal to 2, then the magnitude would be square root of 6 h bar, and you could have 1, 0, or negative 1. So there are 3 different angles that it could have with respect to the z-axis, and so on. So you should know how to produce these angular momentum quantum numbers. That's and what the values of the angular momentum are for each of the quantum numbers, and the orientation potentially. So that gives you the idea of angular momentum, but it turns out that there's a further complication to this. There's the idea of spin. This didn't necessarily have to be true, but electrons, it turns out, have spin. And we discovered that, and we talked about this last week. Electrons have spin, and the reason they have spin is, the reason we know that they have spin is because the Stern and Gerlach experiment observed that electrons in a non-uniform magnetic field get deflected. One goes up, one goes down, corresponding to how their magnetic moment is aligned or anti-aligned with the non-uniform field. And we discovered then, since they go up and down, but not up, down, and through the middle, that indicates that the angular momentum can either be up or down, and that means that there is another quantum number to talk about here. There's the spin, the intrinsic angular momentum that electrons have. Spin is always a half, and then m sub, and we call it now m sub s. The magnetic, this is the orbital. We oftentimes, once we discovered spin, they would call this m sub l. They originally called it m, but now we're going to say this is the m associated with the orbital motion, and this is the m associated with the spin of the electron. So this could be plus or minus a half. Okay, so, and this is a spin quantum number, not capital S. This is little s. Okay, so now the state of an electron in the hydrogen atom actually has 5 quantum numbers associated with it. N corresponds to, it tells you something about the radial distribution of the electron. N is the principal quantum number. It's the main quantum number when asking about, well, what's the energy of this electron? And it's 1, 2, 3, 4, 5, any old integer that's greater than 0. The orbital angular momentum, this is like, all right, on average, as the electron orbits around, what angular momentum does it have? Well, that could go from 0 up to n minus 1. M sub L is the magnetic quantum number associated with the orbital motion of the electron. It goes from negative L to positive L. The electron also has a spin. It's always half spin, but the orientation that it has could either be, spin up or spin down. It's the orientation of the spin relative to the z-axis, for instance. So that's how that works. That's how that looks. And so you could have either spin up or spin down. So these 5 quantum numbers specify the state of an electron in the hydrogen atom. And there we go. All right, now with spin comes the idea that quantum numbers, like the spin quantum number, imply different characteristics for wave functions that have different styles of spin. Electrons have spin a half, but other quanta might not have spin a half. They might have spin 3 halves. They might have spin 1. They might have spin 0. They might have spin 2. They might have spin 5 halves. I mean, there's all sorts of different, spins that particles might have. Electrons have spin 1 half. But Pauli also noticed that these quanta don't come with name tags. I don't know which one of these parts. They're all indistinguishable from one another. So the Pauli exclusion principle arises from the fact that the probability distribution should be the same if I interchange the 2 particles. So particle 1 is actually particle number 2, and particle number 2 is actually particle 1. In other words, the probability distribution should be the same under interchange of the 2 particles that are involved. Under interchange of any pair of particles, in fact. And that means that our wave functions, which we have written about previously, if we're talking about indistinguishable quanta and multiple particles, that they either need to be symmetric wave functions under interchange of the particles, or they need to be antisymmetric, because when I square the wave function, if I get negative the wave function, it's antisymmetric, but when I square it, that still gives me the same probability distribution. So they have to be either symmetric or antisymmetric. And that's when Pauli then figured out that the wave function for particles that have spin 1/2, like electrons, needs to be antisymmetric. And that meant, what Pauli found out, was that wave function goes to 0 always if the quantum numbers which define that state are identical. So no two particles that have identical quantum numbers can exist in the same state. And that has profound implications for applying the hydrogen atom potential to a broader situation where I have more particles. And this is where we started to build the periodic table. So the outcome of this then is the energy that I have to fill. The ground state of any atom then is fill the energy associated with all of the quantum numbers that have the lowest quantum values. Okay, whose quantum numbers correspond to the lowest energy. So the hydrogen atom is the simplest. The ground state of the hydrogen atom is 1, 0, 0, 1/2, and then it could be either plus 1/2 or minus 1/2. Doesn't matter which. Okay, spin up or spin down. It turns out that electron orbiting around actually causes it to be want to be anti-line. That's the lower energy state. So, they want to be aligned. That's the higher energy state, but it's a really small difference. Okay, so that's one thing that happens. Then you say, well, let's add a second electron. Well, it can't have the same quantum numbers as the first electron. The first electron in the hydrogen atom was 1, 0, 0, 1/2, and plus 1/2. That's the ground state. In helium, I add a second electron. But it's 1, 0, 0, 1/2, negative 1/2, spin down. Slightly higher energy to have it anti-aligned, it turns out. With the current that's produced by the motion of the electron. Okay, so that's that. And notice that sort of fills the possibilities of the 1, 0, 0 state. I could have plus 1/2 and minus 1/2, and that's it. There are no more states. So if I add a third particle, a third electron to my atom, lithium, well, the first two act just like helium, 1, 0, 0, plus 1/2, minus 1/2. Okay? The third electron, though, can't be in a state where n equals 1. It's got to be in n equals 2. Okay, all right. Well, for n equals 2, we know that the angular momentum quantum number could be either 0 or 1, but which one has the lower energy? It turns out that the L equals 0 state has the lower energy. And because the L equals 1 state has actual angular momentum. In other words, it's going to have a higher energy because, on average, it's orbiting around now. So it has some kinetic energy associated with its orbital motion. So the 2, 0, 0 state is a lower energy than the 2, 1, and then something else here for the orbital state. Okay, so there's that. So then I've got the 2, 0, 0, 1/2, plus 1/2 or minus 1/2. Doesn't matter which, it turns out. Beryllium is 2, 0, 0, 1/2, minus 1/2. So now that's full. Then when you add a fifth one, which is, what's fifth? Sodium must be the fifth one. Okay, it's 2. It fills all the ones for beryllium as well, and then it goes, all right, well, after beryllium, what's next? I've got my sodium. So then I go, all right, well, I got 1, 2, 1 is the outermost electron, and then it could be 0 or negative 1 or positive 1, and then 1/2, and either plus or minus 1/2. So I just get more and more complicated. But I have to fill the lowest energy levels first. And that's how we built the periodic table, why the periodic table looks the way that it does. And that sort of explains that. So what do I want you to be able to do with this? I want you to be able to at least explain why this happens and to develop angular momenta, how we add different angular momenta. So I want you to be able to notice that the total angular momentum, which we call capital J, is equal to L plus S. These are capitals. So the angular momentum, the total angular momentum, is the sum of the orbital and the spin. So when you add angular momenta, it kind of depends on what their orientations are here. So for instance, if I have L is equal to 1 and S is equal to a half, which that's true, the possible values J could have is all the way from L plus S all the way down to L minus S. And so it could be J could go from, in this case, 3 halves, or it could be equal to 1 half, if that's true. If L is 2 and S is a half, then it could be 5 halves, 3 halves, or 1 half. Or 5 halves and 3 halves, that's it. And so on and so forth. So I want you to be able to know how to add these angular momentum. What are the possible values for, or sorry, these are, all right, so I get myself mixed up on these two. So let's fix this right now. Let's fix this right now. So this is a little bit of a mistake. I do this sometimes too. I guess I get it mixed up. I don't really get, it's not that it's mixed up, but I forget myself a little bit here. So these are the little l and the little s can go from 1 is 1 and a half. Remember that capital L is the square root of L times L plus 1 times h bar. And the same thing is true of capital S, is S times S plus 1 square root times h bar. So the possible values of little j, so this is the little j, can have values of 3 halves and 1 half. That's not the values of capital J. Capital J would be the square root of j times j plus 1 square root times h bar. So keep in mind that that is going to be true. So please try to distinguish the actual total angular momentum with the total angular momentum quantum number j, because remember they go times the square root of L times L plus 1 or j times j plus 1 or s times s plus 1. So that's a thing that I want to make sure is we're clear on. So styles of problems that you could look at here are, for the exam coming up, you could be looking at angular momentum quantum number addition. And, keep in mind we could have 3 particles. Or we could have 2 particles and they each have angular, orbital momentum and spin momentum. And then it's kind of like adding 4 angular momenta at once. So this can get relatively complicated, but it's not too bad. Just do each part separately, and by that I mean let's look at the situation where this is. I guess I'll just leave that. So just do it in stages. So like for instance, let's say I have 2 particles, 2 electrons. I've got particle 1 and particle 2. What you can do is you can say, well, I'm going to add each of these separately. So I'm going to start with I've got L1, I've got S1, and I could say, well, let's say I tell you what L1 and S1 is, and I tell you what L2 and S2 is. These are the different particles. This is electron 1 and electron 2, for instance. I could say, well, let's add these in. Okay? And when you add these things in, you could just, let's forget about 2 for a second. Let's just do number 1 first. I can say, well, the values here for J1 are from L1 plus S1 all the way, in units of integers of this, all the way down to L1 minus S1 absolute value. So, for instance, let's say I have L equals 0 for L1, and S1, the spin, is always a half. Then the values of little j1 could be from 1/2 to, in units of integers now, from 0 plus a half is a half, and all the way down to, 0 minus a half, which is negative a half, but you take the absolute. So there's actually only one value of j1 you can have. It's a half. Okay, so that would be, a relatively simple one. Let's say that I have a case here where I have 4. L2 is equal to 4, and S2 is because S is always a half. Okay, so now I have, so what would J2 be? So I'm forgetting about this. I've done number 1 now. I know that for this particular problem, it's just a half. J1 has the value only of 1/2. Okay, it's the only value it can have. What about J2? All right, well, J2, so I forget 1 now, and I do 2. And I say, all right, well, I could have 4 plus a half is, let's see, this is 8 halves, so that'd be 9 halves. Because that's L2 plus S2. And then in units of an integer, all the way down to 4 minus a half. All right, so that looks like 7 halves. Oh, okay, all right, 7 halves. All right, fine. And those are the only 2 values. Okay. All right, so those are the only 2 values that are involved. All right, so now that I have these 2 here, I can say, well, what are the combinations that I can get when I add J1 and J2? Well, you got to look at all the possible permutations here. All right, so what about when J2, so I'm going to work up here now. What about when J2 is 9 halves and J1 is 1/2? Well, what are the possible values of J total? Just work them out. So J total, the total angular momentum of all, both of these electrons together. Okay, so if J2 happens to be 9 halves, I go, all right, well, 9 halves, I do the same sort of thing I did here. I do J1 plus J2 all the way down in units of, in integer intervals from J1 plus J2 all the way down to J2 or J1 minus J2 absolute value. All right, so let's see what we get here. So 1/2 plus 9 halves is, I don't know, looks like 10 halves. Looks like 5, doesn't it? I think it is. Let's see. It's 10 halves. It's 5. Okay, so it's 5 is one value you could have, and then the next one down would be, let's look at what the lower bound is, and we'll figure it out. All right, so the lower bound would be 1/2 minus 9 halves, which is negative 4 halves. But we got to take the absolute value. So, I'm sorry, it's 8 halves, so it'd be 4. So that's the lower bound. Well, that's it. It's just 5 and 4. Those are the only 2. Okay, so that's when I take J is equal to 9 halves. Okay, now what about when I take J is equal to 7 halves? Okay, well, J is equal to 7 halves. When I do, what do we have here? I have 7 halves, and I've got plus 1/2. So now I'm forgetting that this one is here. 7 halves plus 1/2 is 8 halves. That looks like 4 again. All right, that's looks like a possibility. And then this one can also have, if I have J is equal to 7 halves, I could go minus a half. Okay, well, that looks like 6 halves. So it looks like 5, 4, and 3 look like our possibilities here. Okay. So those are our possibilities for the total angular momentum. Just by looking at all those possibilities. Okay, so that sort of gives you an example. Look at each individual problem and then add the angular momentum of each one. Okay. Then, so I would regard that as sort of an important highlight, knowing how to do that. And then the excited states of the alkali atoms was another thing that we looked at a little bit. But from my point of view, that is something that is sort of a nice to know for the future, but not necessarily a calculational style problem that I would ask you to do. So that's what I regard to sort of be the highlights of this last unit. I wouldn't necessarily worry too much about those excited states. It's something we talked about, but we didn't do homework problems on or do calculations on. So, so I think that's pretty much it. Don't know if I have anybody watching, but I think that's my exposition on what I think are the highlights of the last unit on chapter 6 and 7. Maggie indicated last week that she thought she would be interested in doing doing solids, so we are going to go into solid state next, which I believe is chapter 10. Yeah, the structure of solids and that sort of stuff. So we're going to start chapter 10 the end of this week. So I'll have lecture notes for Friday posted. The exam is going to work very similarly to how your homework works. There will be 4 problems listed. You are going to do 3 of them, though. In the problem that you choose not to do, please indicate in the text box. Just indicate, I'm not doing this one. Don't grade it. That's not the one. So I'll know which 3 then you were asking me to grade. And then the exam will run from Wednesday morning through, let's see what I can't, let me look at I think I had it for, just want to make sure that I'm giving you the right dates here. It's going to run through Friday, but I'm going to actually post lecture notes for Friday as well. So Friday, the exam will be due at 11:59 p.m. So get your exam in by midnight on Friday, basically. But I will have lecture notes and a homework problem or 2 on Friday to be due on Sunday, kind of like what we usually do with that. So that's the format of the exam, or what I regard to be the highlights for the material we're talking about for this particular exam. So hopefully this was useful to you. If you have questions, that you could still post them in the discussion board over the next day. But once the exam opens up tomorrow morning, I'm not going to take any more questions unless it's a clarification about a problem or something like that. One of the problems on the exams. But I won't take questions because I don't want to be answering your conceptual questions during the exam. Oh, hey Josh, good to see you. There's the possibility, you could be asked to have a reflection transmission problem. That is one of those things, and I didn't talk about it much either. I should have mentioned that as well. But yes, that's a good question. There's the possibility that you might be asked to perform a calculation on the on barrier reflection or transmission, but that would be a little bit pedestrian because it would basically be just plug in the numbers for a particular particular situation, and that's we're a little bit more than that around this. So, but I mean that it's a possibility that one of them could be something like that. Or noticing something interesting there. Any other questions that you might have about what's going to be on the exam or not? Okay. All right. Well, I hope you found it at least a little bit useful about what could be what you could see on the exam. Hopefully things are going okay with y'all, and I really wish we could be doing this in person. It'd be a lot better, but this is the best we can do at this stage of the game. So hopefully the exam goes well for you tomorrow. I expect there won't be too many problems. I've gotten the last couple of weeks of homework, I have gotten graded, and there is a little bit of feedback there for some folks. The only thing, I haven't graded the last problem or the last homework set yet that was due from last Wednesday's material, I guess. So I still have that one to get in, but I should get that by the end of the day. That should be taken care of and be no problem. So, but expect to see that exam up tomorrow by 8 a.m. Just complete it sometime between that time and Friday at midnight, and you should be good to go. Okay, so with that then, I think I will end the stream, and I will wish you good luck on your exam, and then we'll see you next week, if not before. Have a great rest of your day, and stay safe and stay well out there. Goodbye for now.